All right. Welcome back to the session in track 3. We will. We hope you had a great apero just now. Next, Faqeer will talk to us about metamorphic testing, in particular in the context of unsupervised machine learning. And he brought with him a use case from customer segmentation. And testing is important. Oftentimes we don't like testing, and maybe your approach will make testing easier for us and our important applications. Thank you very much, Faqeer. The stage is yours.
Hi, everyone. I'm Faqeer Rehman, a PhD student at Montana State University, working under the supervision of Dr. Clemente Azureta. The topic of my today's presentation is MT4UML, that is metamorphic testing for unsupervised machine learning. First, I will talk about introduction, then the challenges faced in testing machine learning applications, then the background, along with the existing work and its limitations so far. And then I will talk about the proposed approach, along with the results that we have obtained. And at the end, I will talk about conclusion, along with the future work. Well, if we talk about machine learning applications are becoming very popular in different domains, like healthcare, cybersecurity, finance, self-driving cars, and so on. A small bug in the system may lead to catastrophic failure, which can result in both financial and human loss. So it is very important to test these ML applications from multiple perspectives to verify their correctness and enhancing trust on them. However, there are certain challenges associated with testing machine learning applications. The first one is that machine learning applications have a large input space for which they need to be verified. An example can be features like date of birth, height, width, road conditions, and an image. They may all contain any possible valid value. So it becomes really a hard task to verify the correctness or robustness of these ML algorithms for all those possible valid values. Second, the low accuracy of ML model is a composite effect, which can arise from 3 ML components, like the data, or the code that you have written, or the framework or library that you have used to develop your ML model. And third is that testing ML applications seriously suffer from the Oracle problem. Well, Oracle, what is Oracle problem? So first, let me talk about Oracle. Oracle is a mechanism that a software tester uses to verify the output of the program. Oracle problem arises when either you don't have the Oracle available, or if available, but too expensive to apply. Well, if we talk about software engineering is a much mature field as compared to machine learning. And software engineering for machine learning is an emerging research area that focuses on using best practices and methods to better develop, operate, maintain, and deploy your ML systems. So we borrowed this metamorphic testing technique from a software engineering domain and try to apply it to machine learning space to show its effectiveness. Metamorphic testing, instead of verifying the single output of for the input, it uses multiple executions to verify the output. Let me give you an example here. Let's suppose I have a machine learning model. I give an image to this model. It gives me some prediction. But how to ensure or how to validate that the output is correct? So this metamorphic testing technique uses multiple executions to check the correctness and robustness of machine learning model. So in the heart of metamorphic testing, we have metamorphic relations. These metamorphic relations are the necessary characteristics of the program under test that specifies how the output should be changed on changing the related input. Let's try to take an example here. Suppose we have the source input, the original input. We feed this source input to the program under test and obtain some output. Now we use the relation specified in the metamorphic relation, or MR, to generate a follow-up input. We feed this follow-up input to the same program under test and obtain some output. And then we compare both the output to see whether they adhere to the relation specified in the metamorphic relation or not. Let me try to give you an example here. Let's suppose there is a program here that calculates the standard deviation for certain numbers that you give as an input. Let's suppose you give some input, it calculates the standard deviation. Now, what type of MR can we propose? One of the MR that we can propose is that if we multiply all the inputs with -1, the standard deviation should remain the same. If it is not, it means there is some bug in your program. Well, in this research paper, we tested two clustering algorithms. One is k-means clustering, and other one is agglomerative clustering algorithm. Let's try to see first k-means clustering. Well, k-means clustering starts with some initial centroids. Then it calculates the distance from the centroid to all the data points to create the clusters. Then what happens is that it creates the average of the clusters to identify the new centroid. And then it uses that centroid to find the new clusters. This process continues until you identify a cluster that is no more different than the previous one. The second one is agglomerative clustering algorithm that is a bottom-up approach to create a clusters. It treats every data instance as a single cluster, and it merges two clusters based how close they are. It uses some distance measure that can be Euclidean distance and some linkage method that, in our case, which is average linkage method. So it calculates the average of the data points of one cluster to all the data points of another cluster, and then it sees how close they are. The closer one would be merged together. That is how we say it is bottom-up approach to create the clusters. Well, if we talk about the existing solutions in this space, to the best of our knowledge, we are able to find just two research papers that uses this metamorphic testing technique in testing clustering-based algorithms. This research helps the end users to choose the algorithm from a large set of available algorithms that can best fit their needs. However, the following are some limitations that we have found in their work. The first one is that the proposed approach serves only the validation purpose. It only checks whether the algorithms under test meet the general user expectations or not. The second one is that the proposed MRs target the algorithms provided by the Weka tool. It is worth exploring to see which type of MRs can be proposed to equally test some other algorithms provided by some popular Python libraries like scikit-learn. And third, their approach uses unrealistic synthetic 2D data. So in our approach, we try to address these limitations. So first, we took an advantage of GQM, a goal question metric approach, which is a goal-oriented approach, and we have used this approach to frame the research work. In goal question metric, first you identify the goals that you want to achieve. Then for each goal, you identify the research questions that you would like to answer. And for each research question, you identify the metrics that would help you to answer your research questions in a quantifiable manner. If you're able to answer your research questions, it means you have achieved the goal that you have defined at the first step. Well, the research goal that we have identified is to investigate the metamorphic testing technique for testing unsupervised algorithms for the purpose of improving their quality from the perspective of both the end user and the developer in the context of testing k-means and agglomerative clustering algorithm. The first research question that we raised is how effective are the proposed MRs in testing these clustering algorithms under test? And second research question is which algorithm is more stable for performing clustering-related tasks? And the first research metric that we have used to answer those research questions is number of violated MRs. That is simply the count of MRs that have been violated by the clustering algorithms under test. And second one is violation rate that shows the percentage of instances for which your algorithm under test shows violations. If I talk about the contributions that we have made in this research paper, first, we proposed an MT-based approach, a metamorphic testing-based approach, for verification and validation of clustering algorithms under test. Second, we proposed a broad set of 22 metamorphic relations that can broadly be classified into 14 categories that can be used to test these algorithms from both the verification and the validation perspective. Then we refer to the official documentation of scikit-learn and analyze those proposed MRs to provide some reasoning to show whether each of the MR is targeting the verification aspect or the validation aspect. And we also try to answer the question why. Why it is targeting the verification aspect? Why it is targeting the validation aspect? I'm not sure why it automatically goes forward, so sorry for that. And the last one is that to show the effectiveness of the proposed approach, we applied these MRs in testing an open source customer segmentation application that uses multi-dimensional data set to create clusters of different customers. As I mentioned, we proposed a broad set of 22 MRs that can be broadly classified into 14 set of categories. Due to time limitation, it may not be feasible to look into each of the MR, so I refer the interested readers to read the research paper, or maybe we can meet after the presentation to discuss them more. But I will try to cover a couple of them. The first one is duplication of single instance. Suppose you have a source input. You run your algorithm. It gives you some output and creates some clusters. Now this output can be treated as the source output, represented by OS. Now this MR says that if you duplicate a single instance to generate a follow-up input, the output should remain consistent. The second MR is data standardization. So if the existing standardized data is once again standardized, the output should remain consistent. If it is not, it means there is some bug in your program, because this is targeting, this is targeting the verification aspect. Next, as I mentioned that we refer to the official documentation of scikit-learn, try to analyze these 22 MRs and figure out which of them targets the verification aspect and which of them targets the validation aspect. So let's try to see what is meant by verification aspect and what is meant by validation aspect. The MRs targeting the verification aspect aim to check whether the algorithm under test adheres to the specification of the program from the implementation perspective. And the MRs targeting the validation aspect aim to check whether the algorithm under test meets the general user expectations or not. These are the analysis, the reasoning that we have provided for each of the MR, for both the k-means and agglomerative clustering algorithm. Again, it would not be feasible to look into each of them. Let's try to cover a couple of them. Duplication of instance. Suppose we have this data, and this represents the customer data, for example, where 2, 3 customers are assigned to one cluster, and 7, 6, 6, 10 is assigned to different cluster. This is basically a dendrogram that is an output of agglomerative clustering algorithm. And if we break this dendrogram to create 2 clusters, this is how the clusters would look like. Now this MR says that if we duplicate an instance to generate a follow-up input, the output should remain consistent. Consider that these are the customers that were your clustering algorithm created 2 groups, the low-risk customers and the high-risk customers. So if in the follow-up input we duplicate this instance 3 that belongs to low-risk customer, what would happen is that this 2, 3 now would be assigned to the first cluster, that is a high-risk customers. So you can see that we have added a duplicate instance. And in the future, yeah, it is very realistic in data science projects. Your data may undergo through some changes. So now what would happen is that the clustering result would change for the follow-up input. Now what does this mean? Well, we cannot say that there is some implementation bug in the program because the MR is violated. The reason is that this is how the algorithm is implemented. It calculates the average distance between the data points of both the clusters to merge 2 clusters. So what happened is that due to this single instance, this cluster is now more similar to that one. So it is not the bug in the implementation. Instead, it is how the algorithm is implemented. So your program adheres to the specification, but not meeting the general user expectation. Being a user, I don't know how the implementation is done, right? So now this MR cannot be used for verification purposes, but it can be used for validation purposes. The second MR is data standardization. So this MR says that, again, for the source input, you have obtained some output. and that output is represented with some different clusters. Now, this MR says that the follow-up input, if we reapply the standardization step, what would happen is that it will neither change the mean and variance between the data points, nor it would change the distance between the data points. So your data is similar to the previous one, to the source input. So now if your program shows a violation, it means there is a bug. So this MR can now be used for verification and validation. Another example can be like if you shift your features with some constant k, that can be 2, 3, or any number, it will again maintain the same distance between your data points, and the output should remain consistent. Let's try to look into the results that we have obtained. First, we verified the MRs for k-means at 3 levels. Normally, the researchers just try to verify the MRs using the output, using the clusters, whether the clusters are assigned, whether the instances are assigned to the same cluster or not. We propose multiple criteria that can be used to verify MRs. So if we are unable to verify the MR, if we are unable to identify the violation for MR at first criteria or first level, we hope to uncover them during the next one. If we look into 14.2 MR, the same clusters have been assigned, but centroids have been changed, and the nearest point to centroids also changed. So we provided the results, we showed the violation, and along with that, we showed the percentage of violation, the violation rate. That is a metric that we have used to answer our research questions. So here we can see that 10 MRs out of 22 have been violated, and MR 4.3 has a higher violation rate, 57.82%. If we look into agglomerative clustering, well, again, 10 MRs have been violated, and MR 9.3 has a higher violation rate, that's 99.28%. And that answers our first research question, that the proposed MRs are effective in testing the 2 clustering algorithms under test. Second, to answer the second research question, if we look into the results, there is just one MR for k-means that shows a higher violation rate, which is 57.82. But if you look into agglomerative clustering, 5 MRs have shown a higher violation rate. Like if you use a threshold of 90%, those 5 are more than 90%. And that answers our second research question, that in comparison to k-means, agglomerative clustering is more sensitive to changes in the input. And it may not be good for scenarios captured by those violated MRs. Let's try to conclude. Well, first, we propose metamorphic testing-based approach to test the 2 algorithms under test. Second, we proposed a broader set of 22 metamorphic relations that both the practitioners and researchers can take an advantage of to test their algorithms using the proposed MRs. That not only targets the validation aspect or meeting the general user expectation, but it also targets the verification aspect. Then, for testing k-means algorithm, we also propose multiple criteria to verify the MRs. And this also opens a new research direction for researchers to see what type of different criterion can be used to verify the MRs for different available ML algorithms. And our results show that both the algorithms under test exhibit violations for 10 MRs. But in comparison to k-means, agglomerative clustering is more sensitive to changes in the data. And it may not be valid for scenarios captured by those 10 violated MRs. Well, to talk about the future work, first, we aim to explore and develop new criteria that can be used to verify the MRs for agglomerative clustering, similar to what we have proposed for testing k-means. Second, to show the general applicability of the proposed approach, we intend to apply the proposed approach in wide range of different clustering algorithms that is famous among the practitioners and researchers. These are the references that I have used to prepare this presentation. And thank you. If you have any questions, please ask.
Thank you. Any questions from your side? None. Where do you see the most relevant application fields in the future?
Yeah, so right now we have applied it on customer segmentation application. But these MRs are generic enough. They can be equally applied to document clustering or anomaly detection, where the term data point would be replaced with the network instance or the document instance. So it is equally applicable in different domains. The only condition is they should use the k-means and agglomerative clustering algorithm, because we have showed the effectiveness of MRs on these two algorithms. So generalizing the results to other clustering algorithms would be speculative. Yeah.
Okay. Well, there's a question.
Thanks for the very interesting talk. I had a question which is hopefully not too mean, but you showed us this slide where you were testing these MRs between the two different clustering different clustering algorithms, and these to sort of get a feel for what these MRs are. I was wondering if you could sort of qualitatively describe these violated 4.3 and 9.3 cases. What is this telling us about what agglomerative clustering is doing that k-means isn't?
Yep. So the MR 14.3 is related to removal of instance or removal of customer in this sense. So let's suppose you have two clusters. Again, I would like to use the same example, low-risk customers and high-risk customers. So this MR says that if you remove one customer from one of the clusters, either from higher or lower, so what is happening is that the agglomerative clustering is very sensitive to this change. And it is assigning like high risk to the low risk and the low risk to the high risk customers. And the MR 9.3. 9.3 is related to replacement of instance. That if you replace the existing customer, like low-level, low-risk customer, with some other low-risk customer, logically the output should remain consistent. But what is happening is that these algorithms are sensitive to change, especially the agglomerative clustering. It is again assigning the low-risk customer to the higher one and higher one to the lower end.
I would have a follow-up question to that. So in that case with the agglomerative clustering, you were looking at a Euclidean distance between points, and you were looking at a mean as your linkage. I would guess that the results change quite a bit if you change. Let's just keep the metric the same, but if you were to change the linkages, have you looked into that?
Yeah, we didn't test it, but again, from validation perspective, yeah, they would be valid. But for verification, we have to look into the implementation, that how the implementation is done, whether these MRs are equally applicable for verification as well. But for validation, yes, from a general user expectation, yes, this is what we would be expecting, that the result should remain consistent. Yep.
Cool, thanks.
Yep, thank you.
Another question? Otherwise, you'll have a break, and I see you at 3:50 again.
Yeah.